Pastor?
I think it's the same, sir.
Well, guys, you are not really looking very carefully. By saying it's the same, you are forgetting everything that we said about what we mean by frequency. Frequency is the time the signal repeats itself. If you look at the current and the voltage, they are repeating over this interval. You see? So if that frequency is F, if you look at the power signal, is repeating only here. You see, it's repeating right here. Sorry, I wanted a different color. Come on, right? This is the interval. It's repeating. So if this period here is T, the power signal is repeating in T over 2. In half the period, it's repeating. Is that not clear from the drawing?
Now it's clear, sir.
So why can you not see that? It means you have forgotten what frequency is. You see? No, that's what it means, because if you knew what it is, you can't say they are the same. You can only say that when you have forgotten what the definition for frequency is. Frequency relates to the number of repeating cycles per unit time. Surely, if you compare the current and the voltage signal, you'll see that when they go one cycle, the power signal has gone twice. So it means the power signal is actually 2 times the frequency of the voltage or the current. That is point number 1. And then the next question I'm going to ask Sabelo. Sabelo, are you with me?
Yes, I'm with you.
Okay. Can you tell me one thing here, Sabelo? Yeah. The power signal, is it AC? Is it DC?
It's DC, sir.
Somebody else? CC? I want people to answer quickly so we can move fast.
It's positive pulsating DC, sir.
Okay. Who is talking?
Sibonginkosi.
Bonginkosi, you're 100% right.
Sure.
It is not changing sign. It is pulsating. You know, it is varying in magnitude, but it is not an AC signal because it doesn't go positive, negative, positive, negative. It stays positive, although it is changing in value. All right? Now, if you take a heater, I'm sure all of you have been to the lab, right? If you take a resistor and you put an AC source, now you know that this is the type of signal. This AC resistor, this resistor here, if it's a heater, it's surely going to heat up and give power. And ESCOM, Tequini, is going to bill you, which means this power here, though it is pulsating, now the pulsation, remember, if the signal of voltage and current is 50 hertz, the power signal will be having a frequency of 100 hertz. So it's going through this purple wave 100 times in a second. It has an average value. That's why the heater, the kettle, the stove is going to heat up and cook our meals. So the next point I want to illustrate is how...
Sorry, sir.
Yes.
Can you please tell us where should we find those videos that you upload them on Blackboard or
Can we go through this?
Office?
You can just keep that question to the end, right?
Okay.
Yeah, it's sort of a deviation. Let's stay with what we are doing here. When we come to the end or at the beginning, then you can ask those things, right? I can't interrupt the lecture now and talk about something else. So I was saying we need to actually find the average, all right? Now, the average power, I'm going to write it like this. P bar is actually equals to 1 over the period, right? This period for the power signal. I'm just using T, but it is actually the period of this, the purple wave from this 0 to T of PT dt. This is from maths. That is how you find the average power of a signal. Now, can we do that? Right, let's do it so that we get somewhere. PT is equals to V peak, I peak. I'm going to write in brackets here and come back to that, right? Now let's look at sine squared. Sine squared, sorry. Write it like this. Sine squared omega t, right, can be broken down using this relationship. We can write this as cos, right, omega t plus omega t. This is like saying cos A plus B, which is going to give us cos A, cos B. Because A and B are the same, this will give us cos squared omega t minus sine A, sine B. But A and B are the same, so this will give us sine squared omega t, like that. Now, you also know from Pythagoras that cos squared omega t plus sine squared omega t is equals to 1. In other words, we can write cos squared omega t is equals to 1 minus sine squared omega t, like that. Therefore, here, in this equation here, we can replace the cos term by 1 minus sine squared t, which gives us now, on the left-hand side, I'm going to write cos omega t plus omega t is just 2 omega t is equals to, I now substitute this for cos, I'm going to get 1 minus 2 sine squared omega t, like that. You see? So now I'm going to make sine squared the subject of this equation. I'm going to rearrange and bring my sine over here. So I'm going to write sine squared omega t is equals to 1 minus cos 2 omega t all divided by 2, right? So let me number this equation. I'll call this one 2 and this one 1. So now I'm going to take 2 and replace it. Remember, 2 is just this equation. V peak I peak sine squared omega t. I found out that sine squared omega t is actually 1 minus, right, cos 2 omega t divided by 2, right, all over 2, like that, right? I'm going to rewrite equation 1 at the bottom here, taking out the brackets and separating it into 2 terms. So I'll have PT is equals to, the first term is going to be V peak I peak times 1 divided by 2. So I'll write it like this, over 2, right? Then minus V peak I peak cos 2 omega t divided by 2 minus V peak I peak over 2 cos 2 omega t. Now look at this equation from what we have said earlier on. If I go back here, the purple curve is our power curve. And this actually is the equation for that power curve. And this integral here, which I have here, is defining the power, what we call the average power. But we can see from here that if we want the average power, it will have to be the average of this plus the average of that. But this signal here is a sinusoidal signal. It is at twice the frequency. Any signal which is a function of cos n omega t, right, where n is an integer. If you do it like this, this is your cos. If you take the integral of that cos over a period, this area on top plus that is equal to the area at the bottom, so that goes to 0. So this term here with a cosine times 2 omega t, it is only telling us that the power signal, as has been correctly answered, is a pulsating sinusoidal components whose value over a full cycle is 0, the average value. But the actual average power coming from the AC source is given by this term here. So we can actually write this as V peak I peak over root 2. That is the average power that comes from the AC source. That is the power that is actually used by this resistor here. And that's what we see when we plug in a kettle, a stove, a geyser, or whatever to an AC source. This is the average power. It's a V peak, I peak divided by 2. That component here is manifest in this curve. There's an AC, but the average value for this is 0. So we only talk about this. Now, the other thing of interest in this equation is when we rewrite this equation in this form now. V peak over root 2 times I peak divided by root 2. We have not changed here, you see, because this is a multiplication. Root 2 times root 2 still gives us 2. But why I've done that is to introduce another term. The two quantities which I have now separated by those brackets. The first one is what we call the root mean square voltage, RMS. And the second one is what we call the root mean square current, RMS. And this gives you the power, average power from an AC source. The root mean square voltage times the root mean square current gives the average power. It is resembling this equation here, if you go back to where we started, right? It's resembling that equation. That is why we define the root mean square current and the root mean square voltage. So you may ask, what is the root mean square voltage? What is the root mean square current? Well, it's nothing but this. Is the peak voltage divided by, peak current. Peak current here at the top divided by root 2. Similarly, the root mean square voltage is equals to the peak voltage divided by root 2. Right? So those two parameters are very important in AC calculations. In most cases, when you say the supply from ESCOM, if you are talking about two single phase, we always say it's 220 volts. That 220 volts is actually a root mean square voltage. It's not the peak voltage, so you should know from now, right? It's a root mean square voltage. If you want the peak voltage, then you would have to multiply 220 times root 2, which gives you about 311. So the peak voltage on the plug, where you plug in your radio, TV, this and the other, is actually about 311 volts. That is the peak of the AC voltage that comes to that point. But ordinarily, we don't worry about that peak. We don't talk about it. We actually do our calculations using the root mean square AC quantities. That means voltage or current. All right? So now, how would you understand this equation? Well, compare in a DC case. I'm writing this for a DC now. We have these two equations, all right? Let me do it like this nicely. The top one is AC, and the bottom one is DC. You see that? So, what am I saying? If I've got a DC source of 100 volts, and it giving, I have a current of 10 amp, the power that I'm going to have is 1000 watts. If I have an AC source with a root mean square voltage of 100 and a root mean square current of 10 amp, then I'm going to get the same power. which is 1000 watts. So in other words, you can think of the root mean square voltage and current as equivalent DC values that will give exactly the same amount of power if you took that root mean square voltage or current and converted it to a DC, right? So the root mean square voltage will give the same power as a DC source of the same magnitude. But if I told you that the root mean square voltage is 100 volts and the root mean square current is 10 amps, you should know that the peak voltage in case of 100 will be 100 times 1.4, which is square root of 2. It will be about 140. The same for the current. It will be about 1.4 times 10, 14 amps. Those will be the peak values of the current, right? But on average, that is going to give the same amount of power connected to a resistor as a DC source with 100 volts and giving out 10 amps. Are there any questions so far? Any questions so far?
SM.
Mm-hmm.
Yeah. Now say if the power, the AC current. No. That is fine, sir. I wanted to ask if the AC current is given in a form of a sinusoidal, then you can pick a peak current from that equation. It's fine, sir.
Yes, you should.
Yeah.
Mm-hmm. But remember, I said most of the time, from now on, you should understand that when we talk about AC in general, we don't actually refer to the peak current. We refer to the root mean square values.
Oh, okay.
So when you hear Mr. Nzimande saying you are going to use 32 volts in the lab, he's not talking about the peak voltage. It's 32 root mean square voltage.
Okay.
Yeah, he will not say it's 32 root mean square voltage. He won't say that. He will just say 32. But you must understand now that it's root mean square voltage. Unless I tell you otherwise in a question, right? If I give you the equation like this, you see, if I give you that Vt is equal to V peak sine omega, and then I say calculate the power that is used in the resistor. If you don't change that peak value to a root mean square, but you carry on and multiply V peak and I peak and not divide by 2, then your answer will be wrong. The correct one is V peak, I peak divided by 2. But if you are given root mean square value, that root 2 at the bottom disappears. So the equation takes the form of VI, which you already know from Eng 1. Are you with me?
Yes.
Yes, sir.
Okay, I will continue. Now, we have looked at the case of a resistor, right? There, the circuit is a resistor. I'll now revert back to a general case. I'll revert back to a general case. Now, this is a voltage. I'm now using phasors. Remember, this is AC analysis. So I'm now going to use phasors. And this whole thing here I'm now going to say it's an impedance. It has a magnitude and it has an angle, right? That is general. Are you with me?
Yes.
Yeah. So get me correct here, right? You must understand this very loud and clear. I have said in general calculations, if nothing is said about peak voltage or whatever, you can assume that whatever voltage is given is an RMS value. Now, the point I want you to be clear about, in most cases, when we talk about phasors, for example, if I want to express this voltage here in terms of its phasor, the strictly correct thing is to express this quantity here as the peak value. That is the strictly correct thing. But in calculations, we are not interested in most cases with the peak value. We are interested with RMS values. So you'll see that we normally use this RMS angle, whatever, right? We'll write the phasor as this with the RMS value. Now, it does not cause any problem as long as you understand that the peak value will be this quantity here where I'm hovering on times √2. If I put √2 here, then that is a peak value. But for calculation purposes, we normally drop this because we are interested with the RMS values. So you'll see that from now on, when I'm writing phasors, I expect you to have that understanding, but strictly, you must realize that this should be a peak, right? But it falls
Yes.
away from now.
Can I ask something before we
Sure.
move?
Mm-hmm.
That VRMS is same as VS. Or it's two different
Remember,
things.
VS is just representing a source. VS is like this. VS, we are just saying a source. That S stands for source. VS can be like this, V peak sign, omega T. That's VS, right? VS is just the time domain expression for all this. Or if you want to write it in phasor form, you can write it like that, right? It's just a symbol, it's a notation. It's got nothing to do with peak or RMS. If I say what is the RMS for VS, then you are going to tell it's V peak divided by √T. You see? Are you with me?
Yes, that's why at the beginning I asked you this question, but to continue, maybe I will get some knowledge on
No,
this.
you were going ahead of us, you see? You were going ahead of us. I think I remember I said, no, I don't want to speak about that at this minute. You see? I did not speak
Yes.
about it because I knew I was going to come to this point and put everything together. But I'm going to take away this thing here. Right? Now, the same analysis that we have done here using the cosine and the sine and what, we can also do that when Z is a general impedance. But because of the complexity that is brought by the angle into our expressions for current, we find that it's easier to illustrate the next point using complex phasors. But if you are keen to see it from fundamentals, the way that I've done it here, I can refer you to some material. In fact, your notes, the PDF handout on Blackboard, it does show the next part which I want to explain using phasors. It does explain it this way and come to the same conclusion, but it's a lot of manipulation and things like that. And I'm trying to get somewhere before our time runs out. So just understand it this way, and you know that if you had to do it this way, you would follow exactly the same procedure, only that you are now going to deal with a more complicated mathematical expression, right? So now the starting point which I'm going to say here is that if we want our current, right, our phasor current is simply going to be the voltage divided by the impedance. That is why I did not answer, I think it's Sabelo at the beginning, when I said, no, tell me your problem, you see. At this stage, Sabelo, I don't expect you to be asking a question to say, I don't know. Even in the laboratories, you have been told this. You see, it's voltage divided by the impedance. And what do you have in the circuit? You have got a resistor and an inductor. You cannot tell me that now. You cannot define what Z is after all the work that we have done. You should have been able to do that. That's why I wanted to understand where are you lost? Because that at this stage of our study is very, very simple. No one should be struggling with that. So this is where we are now. Now, the way I'm going to handle this is I'm going to write this as IRMS. I've already told you, angle minus theta, right? This impedance here, when you divide and the current is going to give you minus, the voltage is 0. Now, what I want to say very quickly is that when we do AC analysis, you'll see that when we define power, P, it is not going to be exactly P. Now, what we are going to have on the left-hand side, I will define it after the right-hand side. Now here, generally, we are going to say VRMS angle 0 times the current, this one now, IRMS times the angle, not times the angle, theta. Now here this, we will come to this later on. When the situation has got a complex impedance, the correct conventional way of writing the power equation, just this one here, just this, is to take the conjugate of the current. So we take the conjugate, that star there represents conjugate. If you have got a complex number, which is say 1 plus J2, the conjugate is simply 1 minus J2. You change the sign of the imaginary. If it's written in polar form, you change the sign of the angle, right? So now I can take this star out by writing this or conjugating as V RMS and then I RMS angle theta. I've taken the conjugate because you change the sign. Now this here, the quantity on the right hand side, as you can see, it is in polar form, right? Please understand, I've avoided to do it the previous way because there's a lot of manipulation. I'm saving on time, but that can be shown. I've referred to you where it is. This here, can be written in a rectangular form as r cos theta plus j r sine theta, where r is simply the product of VRMS times IRMS. So I'll write this as VRMS IRMS cos theta plus J VRMS IRMS sine theta, right? Now notice that this quantity here, or the expression rather on the right hand side, has got an imaginary component and has got a real component. The symbol P is reserved to represent the real component. And therefore, we define a new symbol for what we are seeing here. And this we are going to call S. So this is the real component, which we represent by P. This here is the imaginary component, which we represent by Q. So the power, when the impedance is no more a pure resistor, has got two components, P and Q. P is the one that we measure in watts. So P is the one that we measure in watts. Q is an imaginary component which we measure in units of volt, ampere, voltage, ampere current, reactive. And the left-hand side is a power quantity which we measure in units of volt ampere, just like that. So S, P, Q. This part here is called reactive power. This part here is the real power. And this part here is called apparent power. So there's reactive power Q, real power P, apparent power S. Right? And obviously, you can see by equating this quantity here with that, this quantity here with that, that P is simply VRMS IRMS cos theta, and Q is equals to VRMS IRMS sine theta. The apparent power S is given by VRMS times IRMS. And the ratio cos theta is called the power factor. We'll explain it later. Power factor right? So those are the parameters that define the apparent power. Now here I've used Z as an impedance which is inductive. If my impedance was capacitive, you'll find that this here will be negative. So in general, this is plus or minus. It is plus for an inductor, and it's minus for a capacitor. So the reactive power component for a capacitor is negative, and for an inductor is positive. Apparent power, real power, reactive power. Very important parameters when we speak about the operation of electrical systems. Now, to conclude today's section, if you look at this equation here, right? Let me put a small subheading, and I'll call this power triangle. Power triangle. We now know that S apparent power is equals to P plus or minus JQ. If I do my normal XY axis, this is imaginary, this is real. Change color. These three quantities here can be shown in a right angle triangle because this is just like a point on the complex plane. So if here I've got S, this is S now, then down here, this point, I'll have P. So P will be this distance here. And up here, I'll have Q, which is this distance from there to there. This is Q. This is a right angle. This angle here will be theta. All right? This is a right angle triangle. So we know that Pythagoras magnitude-wise, P squared plus Q squared. That's Pythagoras. That's squared, right? And then we can also write cos theta. You remember we said this is the power factor, is equals to, from trigonometry, this is this distance divided by S. So it's P over S, right? That is your power factor. If the load is capacitive, then your Q would be down here, minus Q. And then your S will be like this. This will still be a right angle. So this is S, and this will also be your theta, right? So in this case, you'll have S is equals to P minus JQ. And that is capacitive. It's a capacitor, cap, capacitive load. This relationship here still apply, meaning that if you have got P and Q, you can find S. Or in general, if you have got any two of these, then the rest of them are defined. You can calculate them from that power triangle. This is what we call the power triangle. All right? Now, let me close by a small example. All right? Let's say a small example here. Example. All right. Let's see if we can find a nice example. No, come on. That's not my screen. That one. Okay, still sharing. Now, let's say this is a circuit. There is a circuit, and the voltage here, I'm just saying, is 220 volts. And then there is a resistor there. Let's say this is 20 ohms. Then there is a capacitor there. And the capacitor is 60 microfarad, like that, right? Let me change it to 80. I want 80 microfarad. Then the question is, find S, the apparent power supplied by the source. Find S, so that will be volt ampere, the apparent power supplied by the source. Now remember, this is RMS voltage. So, and if I didn't say anything here, you should know that my frequency is 50. That is what is reasonable to assume, because that's our frequency in the country, right? Unless otherwise specified. So, my friend, Sabelo,
Yes.
the impedance, my friend, is 20 minus JXC, right? XC is simply 1 over omega C, and this is 1 over 2 pi
the point line
times 50 times 80 microfarad. Right, Sabelo, can you calculate that number and give me? 2 pi times 50 times 80 microfarad. Sabelo.
Okay, my calculator time. That is 80 macro.
Microfarad.
That is 0.04.
Is 39.78.
That's correct. 39.78.
78.
79.
Yes.
Yes, sir.
So ZC is minus J, 39. 39.8 by itself is the reactance. So Z for the circuit is 20 minus J, 39.8. Therefore, the current phase is going to be 220 angle 0 divided by 20. Please switch off your mic. J, 39.8. Sabelo, give me that division, that number.
Okay, Sam. Let me.
Yeah.
Oh, okay. So the answer is 4,5. It's called is 4,94. And the angle is 63,32.
Very good. You can now see that you are answered, right? So this one is 4.93. I'm just repeating 4.9. Come on. 93 angle 63.3 degrees amp. Notice that the current phasor is a positive angle, and it's a capacitive circuit. We expect that the current leads the voltage. Therefore, the apparent power is actually now V. Remember, this is RMS. I may not write here, but that's what it is. V RMS, I RMS, right? Conjugate. So this will now be 220 angle 0 times. The conjugate of this, I must just change the sign of that angle. So it will be 4.93 angle minus 63.3 degrees. So again, that multiplication, Sabelo, give us the number. I think it's 1086, right? I'll just say 1087 angle minus 63.3 degrees. If I asked you for the real and the imaginary power, you would convert this polar form. This is volt ampere, the units. You would convert this polar form to rectangular form, and you will get. Sabelo, are we together?
Yes, sir. We are together.
You did not give me the number.
Yes, I got that number, 1087.
Okay, let's change to polar form now.
So when I'm changing it
Sorry,
to
to
polar form,
rectangular.
that is 487,33 minus 968,95 J.
Right. So for this source, the real power is 488.4 watts. The imaginary power Q is 468.6 volt ampere VA reactive. Right. If I had asked for power factor, then you would say it's P divided by S. Right? It's P divided by S. Is the magnitude. So P is 488.4 and S is 1087, the magnitude. And then that will give you divided by 10, 0.45. Or we can say 45%. We can express power factor as a fraction, as a decimal fraction like this, 0, or in percentage like that, 45%, right? If you wanted to draw the power triangle, this is a capacitive load. So I would draw my triangle like this. This is 1087. I would write volt ampere. The real one is 488.3 watts. And then this one is 968.6 volt ampere reactive. and then I would show that angle. Right? I'll just simply take the arc cosine of 0.45. That will be about 63.3, the same angle we have here, 63.3 degrees. That is the power angle, right? I'll leave you with another example. Example 2.
Before
Sorry?
we move, sir. Before we move, can you go back, Molenyan? From where you introduced that conjugate, that star thing, that S is equal to VRMS, IRMS star. So it's where I'm confused. It's where I get lost.
Where are you lost?
That what ngizothini ngesingisi kodwa ubona ngani sekuthi kumele ufake leso star?
Okay. Now, hear this, right? In a DC circuit, I said that power in general is that. You remember this?
Yes, I remember this one.
Then we went to the resistor in an RC, in a purely resistive circuit, and we came to this conclusion here, right? Like that. You remember that?
This one.
Yes.
Oh, yeah. Yeah.
That's when I explained here, right? Yeah. Can you see that?
Yes, yeah.
Right. Then from there, I then said, okay, let's move now. Remember here, our circuit was a pure resistor. There, Z is equals to R.
Yes.
The second case or second scenario, I then said, no, Z is no longer just R. Z is either inductive or capacitive. And I wrote it like this in general.
Oh, yeah.
It is at this point where I said, now look, I am not going to go through the analysis, involving cosine and things like that and so forth. I introduced to you that by convention, to be consistent, and I said I would explain it later, I still haven't come to that point, is that the correct way of writing the power equation, I was borrowing on this now. You see this?
Yes.
Because we arrived at this for a pure resistor. From here, I then jumped straight. I said for a general impedance, what a voltage times a current now. Remember, the current doesn't have an angle of Z, 0 anymore, as in a resistor. Right? That is where I said to be consistent with convention, we take the conjugate of the current. It's the same expression as this, but the only change is we conjugate. Now here I could have shown conjugation, but it won't change anything because there is no angle. Because I said conjugate, you negate the angle. You change the sign of the angle. So I didn't talk about conjugation here. You see that? There is no angle.
Yes, sir.
Yeah. So here in general, that's where you introduce the change of angle, right? I've just given you that as a fact. I did not explain it. I said it's convention. Take it as it is. We'll come back to that later, right? So that is where the conjugation came about. And I explained now, I said the conjugate, if you have expressed your current or any other quantity, if it's in polar form, the conjugate is the same magnitude, but you change the sign of the angle. If it was positive, you change it to negative, or vice versa. It is on this basis that I come to this example, right? Where I now say, now look, the current is this. right? And because the current is that, I'll end up with this expression for the apparent power S. I take the conjugate of the current. It is leading here. The conjugate gives me a negative. That is your negative. And then the rest is the multiplication and the power triangle with this on the negative real x-axis. If you want to show your axis like this, this is below the x-axis where Q is negative. There Q is positive, up. Your 0 point is here. Are you with me?
Yes, so we do conjugate in capacitor, and also we can do this in inductor.
You do it everywhere.
Oh, okay.
Yeah. The issue is the current in a purely resistive load is in phase with the voltage. In other words, the angle is 0. So if the angle is 0, remember the conjugate of complex number. If this is a complex number here, right? The conjugate of a complex number is simply going to be this minus that. Are you with me?
Yes.
It will be 3 minus J3, right? In the example that I've given you, it's of no consequence because there is no angle in the current because it's a pure resistor, as I've given it. Okay? Don't worry, we'll come back to this and then we'll wrap it up when we shall talk about, the inductor, and then we put the picture together. I just wanted to give you an example to close up here, right? Is that Sabelo talking?
Now, that was not me, but... Oh, yeah. The one who's asking question, it was me.
Oh, okay. All right. Sabelo, you are my friend. Is the one who came to the office, are you?
Yes.
When I saw in the Prague yesterday.
Yes.
Okay. No, I now know whom I'm talking to. I just wanted to make sure I can see your picture. Thank you.
Okay.
Sabelo is a good boy. He asks, right? Now let's take this example here. You have 220 again, right? Let's say you've got 20 ohms here. You've got a capacitor. I'll say again, it's 80 microfarad. So you know the impedance is the same as we have calculated. And then over here, I'm going to put an inductor. All right. This is an inductor. The inductor, I'm going to give it a value of 75 millihenry. Right? So you've got, remember the frequency is always right, unless I tell you otherwise. We're using our frequency here. All right? So there is the question. I want you to do me a couple of things here. This voltage here, it's VR. Remember, it's all phasors, right? This is VS, it's phasors, even if I don't write it like that. And then these two, of course, are in parallel. And let's say that voltage is V1. And there's going to be a current here. Let's call this one I1. And there's going to be another current there. let's call this one I2. This current here, I'll call it IS, meaning the source current. Like that. So question number 1, find IS, find VR. These are phasors, right? Even if I don't put that arrow, you should know I want a phasor. I1, I2, this is I2, and V1.
Also calculate the direction. If
Oh, shit. Okay, let's try and put it back together. Like that, and then this one, V1, so this is I2. Right? That's I2, right? That's what you need to find for me. Then the second thing, number 2, find S, P, and Q from the source. 3, draw phasor diagram. Draw the phasor diagram for all these quantities here, right? And then number 4, draw the power triangle. Power triangle, and find the power factor, right? So find those parameters, those voltages, then find P, S, P, Q, draw the phasor diagram. That sign is phi, stands for phasor diagram. Then lastly, draw the power triangle and find the power factor. That's your practice question, right? Now we are having our test 1 online on Wednesday. I think I said 3rd. I'll see how the load shedding is happening. If the news says there is no load shedding, then I'll make the test to be written at the same time by everybody. But if we still have the risk of a load shedding, then I'll see if I can allow a longer interval. But wherever you are, you must know, in case of load shedding, what time is your load shedding, so that whatever times I put here, if they don't suit you, then you have to let me know by email. But I would set it in the event of load shedding, it will be over a long period of time. It can be accessible from morning to 12. So that should be able to accommodate everybody, because the power will not go for half a day in the same area. It will go. But the important thing for you to note is, if there's going to be load shedding, you need to know what time. Don't start writing without knowing, because if power goes off, automatically your work will be submitted. You will not be able to continue. So you need to do it in a time when you know you are free from load shedding. I'm hoping there won't be any load shedding. All right. Then the second announcement is, I did say I would post an assignment. I'm going to do that today. I'm going to put an assignment on Blackboard that will be for assessment for your DP mark. That will be assignment number 1. I'll put instructions on Blackboard. So you follow the instructions, what needs to be done. You will have a couple of days, maybe 2 or so, to submit the assignment online. And that will be that. And then for this coming week, just to see where are we? Are we back online? This or the other? Are we doing contacts? I'm just trying to check the schedule here.
So can you move up a screen a little bit on to right number 2 and page 4?
For you this week, it is this coming week. This is the 4th week now we are entering since we started on Wednesday. So we are going online. It is the S3s and S4s that will be in contact mode. But I did notice in the last weeks that most of those venues are normally available. I think the reason for that is the students in the other faculty, business management, they are probably doing 100% online, so they are not using their venues. But for us, according to the schedule, we are online, right, this coming week. But according to your groups, that means lecture groups, A, B, C for day and A, B for evening. If you want a contact tutorial, you will have to arrange that with me through your class rep. But it must be a class rep talking, not any other student. I cannot handle the volume, but I will listen to the class rep. That does not say you are not going to have your online periods. The online periods will happen for both day and evening students separately. If you want to attend both, you are available. That's your problem. I have nothing, against that. But please note that this coming week, you might be having tests. I know there's electronics 2 test. You are going to have tests for me, but I'll also be available during those online periods. If you want contact in your groups, it can be done by arrangement. I'm still bothered by Group C, but if the guys in Group C are following and reading the lectures, then I have no problem. But I think I haven't seen that group as a group in contact mode. I've been looking for them for some time and they haven't pitched up. Thank you very much. Are there any questions? We have come to the end. Okay, bye. Enjoy the rest of your Sunday.